Hello, everybody, and welcome to the Taiwan Semiconductor webinar. It's 3 o'clock Central European time, and we're starting with our technical rectifier technology webinar here. Before we go on here, in the last minute, people are dialing in. A few housekeeping rules here. There is at the end a Q&A section. The webinar will take about 50 minutes. In that time, there will be afterwards a follow-up email here to request all the slides and the information here. There's also going to be a recording available here for you to listen to afterwards if you want to look at it a little bit more slowly, because the content will be slightly or rather complex here. So let's get going here and let's look at the agenda, what we're trying to achieve today. We're going to talk about the front end of rectifiers, where we're going, where technology is going, and I'm going to specifically talk about 600 volt planar technology here as an example here. We're going to look at topside cooling, which is becoming very common in the industry, or is a big buzzword in the industry here. We're going to look at, we've got all kinds of packages here, and we added a lot of them in the recent years. So we're going to talk a little bit about packaging, product positioning, how each of these packages fit in the grand scheme of things here. And then in the end, we're going to talk a little bit about searches, data sheets, and also actually about simulation here. So at the slide of the thing here, we're doing this in conjunction with the Bodo Systems, where we advertise this webinar. So not everybody may know our company. So 2 minutes about Taiwan Semiconductor. As we read in the introduction of the Bodo email is, we think rectifiers are important. We're about 4.7 billion is the market share alone for rectifiers here. So we're participating in that for more than 40 years. Taiwan Semiconductor is a 40-year-old company in Taiwan here. You can read through all the details of the slide here. I'll just point out to you that we are $261 million last year. Together with the printer division, we're now $500 million company. And the other thing you also need to know is that we're more than 20 years in Europe. Here we've got a Munich office, not just with salespeople and customer service, but also with logistics specialists and also, for example, an automotive quality manager. My name is Jos van Loo. I'm doing the applications and in Europe here, and I will be your presenter today, and I'm part of this European team. Taiwan Semiconductor is known for rectifiers, and we've got 95% of the product portfolio for bridge rectifiers and just general rectifiers, and also TVS. That's our core business. That's what we're going to talk about today here. But we had a big milestone in the company last month, so I'm going to briefly repeat that here. We produced our first N-channel MOSFET using split gate technology in a PDFN 5x6 package here that was automotive qualified, because we're doing that already for more than a year, but we've got our automotive qualification for N-channel MOSFETs here. And we're investing quite a bit now also on the back end internally in Elan here in MOSFETs here. So you gradually see us more and more moving into the MOSFET market, apart from being very well known for rectifiers. And of course, we also have an analog product portfolio here. Let's go to the planar diodes, or the front end here. So we're going to talk about a product portfolio, just one slide. We're going to compare the process or the capabilities with GBP. GBP is the best known process or front end process for rectifiers. It stands for glass passivated pellet, which is a bit of a strange name here, but we'll explain that with a drawing how we come to that name here. We're going to talk about the applications, and we're going to look specifically at power factor correction bypass diodes. So let's go and have a look at the front end here. We introduced in the first quarter a number of 600 volt ultra-fast diodes with 25 nanosecond recovery time here. We introduced them in all the major 8 packages now in the industry, SOD123W, SOD123 with exposed pads, SOD128, and of course the old-time favorites here that are there for more than 30 years here, and also the TO277 here. As usual, you have a die size, and it fits in a number of packages here. So you introduce the whole product range here with all the different die sizes. And we all know by now that you can't get 8 amps out of an SMC package, but we have an 8 amp version just to offer you better efficiency if that is your main concern here. So this is a group of products which we've introduced here, and now we're going to look at their comparison here. And these are all planar diodes. I'll need to repeat this here because we go to the next slide, and we're going to compare them with a GBP diode here, the ES2G. The ES2D, the 200 volt version, is in the business already for 30 years or something like that. The 600 volts versions came a little bit later here. So we're not going to look at all 16 products, but we're just going to look at the 2 amp version in an SMB package here. And I'll circle in red so it's easy to see. On the left, you have the planar device. On the right, you have the GBP device. Let's first look at the VF here. The 1.5 is obviously a significant improvement in 1.7 volts. So the VF and the efficiency due to that is better. The 25 nanoseconds here are better than the 35 nanoseconds. So you have a much faster recovery time. So that's also a big improvement here. Then shorter to the things I haven't circled here, the 2 microamp versus the 10 microamp here. It doesn't look like a lot here, but if you go to higher temperatures, actually you see that the leakage current is significantly better. Leakage current tends to be, in general, associated with reliability. So a lower leakage current is much better. Then some people always wonder about these recovery times here. We measure them using this circuit here, which has got nothing to do with actually what a real circuit looks like in the industry here. That is because 30 or 40 years ago, people actually invented test equipment here. We need to test these things by the billions, and this is a very cheap test circuit here. So everything is characterized using this here. In our new data sheets, however, we do characterize the product a little bit more closer to where you would actually use this product here. A 2 amp diode would be switched off with 200 amps per microsecond here, which is pretty fast here. I know there are IGBTs that do it faster, but it's still a good indication for you. And then, of course, the 2 more important parameters are the reverse recovery current and the reverse recovery charge here, which are characterized as typical values because they will not be tested 100% in mass production. So this is a clear advantage here. I don't think there's any doubt here that these planar diodes are better and the diodes of choice for the future in 600 volt hard switching applications, or any application actually in this case. We'll go a little bit later more in detail about the hard switching versus soft switching in a later slide here. One thing here, if people are a little bit confused about these power diode parameters, we have an application note, AN1006. The link here is at the bottom of the slide here, and most people remember TRR here, but what is important for switching losses in hard switching is the store charge and the peak recovery current. This is dependent on the forward current that you switch it off with and the DIDT. If you switch off with a higher DIDT, the peak will go lower and there will be a more store charge and a bigger peak recovery current here. What is not so well known is that these parameters are temperature dependent. So the QRR and the peak reverse recovery actually have a positive temperature coefficient. So what happens at 25 degrees C is not at all the same as what happens at 125 degrees C. So this is something you need to take care about. So obviously here, to summarize, these planar 600 volt diodes have a better QRR and the recovery current here. They have an improved leakage current. And this is one line actually I would like to say a little bit more about, the improved VF versus TRR. Actually, if you want to make your diode faster, you add more platinum to it. And that actually increases the VF and also increases the leakage current. So there's no such thing as the perfect or ideal diode in silicon. Here, there is always a trade-off between TRR, VF, and the leakage current here. The product actually, the new planar voltage here, 600 volt diodes, are actually the diode of choice now, especially in hard switching applications. So now let's look a little bit more at these hard switching or soft switching applications here, because if you go to our website, and not only to ours, also to everybody's website, there are actually hundreds of fast recovery diodes on that website here. How do I choose the right one, or what is important in this case? I've shown here the circuit here, or the waveforms here, in a power factor correction boost circuit here, because we're talking about 600 volt. That's the most common application here. You have the continuous conduction mode. So the purple one, purple line is the current in the inductor here. And the continuous conduction mode, there's always current in the inductor here. In the discontinuous conduction mode, in the DCM mode at the end, the current actually goes to 0 before it starts again here. And then you have the critical conduction mode, which is just in between here. The current, of course, in the diode conducts here. I'm going to go to the bottom slide here. It turns on in this part of the thing here. The MOSFET is working here. Here, the diode is working here. So it turns on here, and in the discontinuous mode, it actually turns on with a 0 current. So this is soft switching here. The application here is called hard switching, because here the diode is turned off with the current here. So how do you choose the right diode out of the hundreds of ones available here? This is a tricky question, especially since it's also could be a commercial question here. For hard switching, it actually is very simple here. The switching losses are more important than anything else here. So the QRR is more important than the VF here. So these 600 volt diodes here, which we just demonstrated, are just perfect for hard switching here. For soft switching, it becomes a little bit more complex here. The VF becomes more important, and the conduction losses become more important here. The TRR is important here, but by improving it, you will not reduce the switching losses. It just has to be fast enough here. And then, of course, you're going to increase the VF by adding the platinum here. So in soft switching, it's slightly more complex here. The VF becomes more important here. So this is something you need to keep in mind and here when you make your choice for out of the hundreds of fast diodes available on the market here. The next slide shows actually a screenshot from our website here. And you can read here with me, fast recovery diode, high efficient recovery, super fast, and ultra fast here. What do those things mean? Well, they're actually more like marketing names than really scientific names here. There is a difference between all these fast diodes. Some of them use epi, some of them don't use epi. That actually has an impact on cost. It's as simple as that here. And some of them have different diffusion techniques, which have also an influence on the TRR here. So there is a difference here in the manufacturing techniques used for these diodes. But I wouldn't say that what we have on the website or what anybody has on the website is necessarily a scientific grouping of these diodes here. So if you're on soft switching here, you select your voltage, 600 volt. In the case of Taiwan Semiconductor, you have 357 entries. You can actually reduce it a little bit here by looking at the Q101 qualified or not, whether you need that or not here. That will roughly half the amount of entries here. And then you select one or two packages you like here or currents that you think are relevant for you. You export it to Excel, and then you make a VF versus TRR comparison here. So that's one way of choosing your right diode here. And then, of course, you may want to inquire about the price, because you will probably get products here in the case of soft switching, which have different manufacturing techniques, and obviously, as a result, the different cost sections here. So soft switching can be a little bit more complex than hard switching here to switch to use your diode here. The next slide here is linked to 600 volt diodes here, and it's linked to the power factor correction circuit here. So what we're talking about sometimes is the D1 here, the diode here, the D1 here, which is a hard switch diode. Well, if it's, if the power is up 50, we're talking about 100 or 200 watt here, because in lower power, you don't need this bypass diode here. So what happens is you have a hard switch, the PFC diode here, that is actually the energy is contained in the output capacitor here. You have the input protection circuit, the EMI filter, and the bridge rectifier here before that. What happens is that during startup here, this capacitor is empty, so you have a huge surge current here. There are two things to remember about this. If the D1 is silicon carbide diode, actually they don't like surge currents here. Silicon carbide has a positive temperature coefficient on the VF, and it also usually is made with very small die here. So, and the surge current is very limited. So you could destroy the silicon carbide diode. The second thing that also could happen is that this inductor and all this scheme is set up for the normal operation here. And if you have a huge inrush current here, there could be oscillations that could also actually destroy your D1 here. So you have a bypass diode in every PFC circuit over a certain power level here, which just bypasses this thing, and the only thing that it does is conduct during a few cycles, or one cycle if you don't have soft start, and charge this capacitor. So it actually is pretty useless here. It only stands there for a very short period of time, and it's actually only used during startup here. So the only thing that's important here is its surge rating here. And so that's why actually the most common one used in this application, is the S3M device in a SMC package here. So because it is actually used just in the startup phase here, we actually add the 1 millisecond time rating for a surge here. Why is that important? Most of the time, in most applications, when you do charge a capacitor, you're somewhere in the area of a couple of 100 microseconds, 200 microseconds, 300 microseconds, something like that here. So if you have your surge rating at 1 millisecond, you can actually be pretty sure here by adding this to the data sheet here. You don't have to think about, I've got a 200 amp surge here. Is this 100 amp surge rating okay? No, you can look at, it passes the 230 amp at 1 millisecond, so I'm gonna be actually okay in my application. So this is just an added security we did for actually the designer in his circuits. Here we go. Let's talk a little bit more in detail about front-end processes here. On the left-hand side, you have the planar process. This is what you learn actually at school, right? So everybody's familiar with how these planar processes look like. This GBP process is just a little bit different here, right? So what you see here, the green thing here is glass. And over that, you have an oxide here, and the orange thing here is the metallization here. As you can tell here, this is maybe a little bit more efficient here, point of view of active area that you use here, whereas this groove here, this thing what you etch out here, is actually uses quite a bit of space here on the IC here. And also what actually here, to put this in perspective, the grooves are a little bit deep here. So what this does actually here is cause sometimes problems for wafer breakage here. So what you'll see is that GBP is rarely used after over 5 inch because of that, because you cannot, you have too much problems with wafer breakage here. The planar diodes here, actually, you can scale up 8 inch or whatever you want to here. So that is a factor here, so you can do that here. Nevertheless, GBP is a great process that will be used for a longer period of time and has been used for 30 years here. When I started to the webinar, I said we were making about 4.7 billion rectifiers, or the market is $4.7 billion a year or something. It's not bad to assume, or something as an average number, something like an ASP of 4.7 cents for a rectifier. So that means that we're making 100 billion rectifiers a year. So that's a lot of them. They see 100 volts, 1,000 volts, or a lot of current and that type of stuff. So they are usually exposed to a high temperature in the circuit. So it's a very good process. And I would say that here, before we go to the overview slide, a little bit more on this GBP process. I'm not going to go in detail here. This is just as an added slide here. But what you'll see is here, we forgot on the slide here where the second photolithographic step is here. It's a 3-mask process here with three photolithographic steps here, or masks here. And actually also here, there are ways here to make this automotive capable, or improve the automotive capability here, to also come to 0 defects with this device here. So it is possible to do that with this device here. So when we go to the summary here, so of the 100 billion rectifiers made every year, I would say that easily 80 or more billion are made during this GBP process here. And rectifiers in general are low in any parameter analysis of field failures here. It's a cost-efficient process. That's why I would be here for forever here. It's long established. There are different versions of this GBP process that you need to be aware of, and it actually meets most demands. So there is no real need to switch from GBP to a planar process, unless of course you can make better, fast recovery diodes, which the planar process can here. The planar process is more automated, so it may appeal to automotive auditors. So that is one area where it's actually very popular here. It's got lower leakage current, sometimes difficult to measure, but at 125 degrees C, and higher voltage, sometimes visible to the user here. It may have a lower VF. You can also, all planar processes tend to be epi, but some GBP processes are also epi here, so there is the capabilities is possible for both here. Because they use the chip more efficiently, they have a higher active area, you can get a higher current density in the package here. So that is another area where they have advantages here. You can also scale it up maybe to higher voltages, over 1000 volts, maybe easier, and you can do ion implantation here. So those are the two key processes here for our 100 billion rectifiers here. So both are important, both will be there. We have both, and maybe grow a little bit more on planar than GBP, but we certainly had 30 good years with the GBP process and high reliability products here. I put the star here, the question mark here, silicon carbide here. It's not going to replace silicon anytime soon. As we know, the advantage is it's a silicon carbide Schottky diode, so essentially it has no minority carriers. So essentially, it's of course the improvements in hard switching applications where it will improve the efficiency here, and it's the only way to improve the efficiency here. But the cost difference is very big, and we can read press releases nearly every day where you can tell that the silicon carbide will be capable of closing the gap with standard silicon anytime soon. Nevertheless, they are popular in power factor correction and also in automotive applications, where, for example, totem pole, PFC, and that type of stuff is becoming more and more and gradually increasing market share. And we will also introduce silicon carbide diodes later on. So here we are. That was the section, I think, about the front-end processes. So now let's go. We're in the middle somewhere. So let's go to the back end here. Let's go to topside cooling first here. And we're introducing a new package here. I'm going to go to this immediately. Topside cooling, so TSC here. So we're made as a company to TSCP here, our new package, the name of our new package. So actually we are made to introduce a new topside cooling package here. This looks a little bit different from any rectifier package you may have seen here. The ratio here is here, the heatsink here is 8.6 to 6.3. That you can compare with 11.9.5 for the total package size here. So you can see that roughly 50% of the package here is on the is a heatsink here on the top side here. The top side is of course the cathode here. You solder the die to the cathode here because that's where the heat loss is, or that's where the heat dissipation is in a rectifier here. Before somebody says here, I've looked at the toll packages for MOSFETs and I like them a little bit better. They've got a higher ratio of the package to the heatsink here. Be aware that we're in high voltage here. So this package is not made for 100 volts or 50 volt products or things like that. This package is made for 60 or 600 volt or similar and things like that. So we have issues with what we call creepage and clearance here, the distance between anode and cathode, that needs to be respected for high voltage here. So this actually influences our package design a lot here and is one of the major differences between rectifiers and, for example, MOSFETs. Of course, high voltage MOSFETs have the same issue here. This, we think, is a very cost-efficient way of producing a topside cool rectifier here. So let's go to the next slide here. The next slide is actually here. Yeah, it's you see those dimensions and people say, how big is that really here? So we just put the slide here and comparing it with a D square pack here, where you see 16 by 9 over 15 by 10 or something like that. So it's similar in footprint performance here, or in size versus G square pack. So that's a good way of actually remembering how big the size of the package is here. So this is, of course, how a topside cooling package works here. You can also drill with a DPAK, you can drill vias and put the thermal vias here and put the heatsink on the other side here. And of course, that adds to the whole performance of the device. the thermal violence and the BCV you need to pass here, plus also maybe it's easier to connect here with this big larger heatsink on the top here than it is maybe on the bottom, maybe connections here on the bottom here. The isolation thermal pad is of course necessary here. You need dielectric isolation because you're working on a 600 volt part here. So that needs to, that's necessarily before you connect it to the heatsink here. As you can tell here, the original design here is for the secondary side in a DC-DC converter, high power DC-DC converter, probably maybe used in onboard charging or similar like that here, but we're obviously can market the product also for our other applications here. That just gives you the initial design here that people were thinking about. The thing that actually comes to mind here is, of course, what is the thermal resistance here? For this, we measured the thermal resistance of both the topside cooling package here and the D-square pack. We used it on infinite heatsink in this case here, and you can see here that the difference in thermal resistance is around 0.9 Kelvin per watt here. So that is substantial here, and that's pretty good. That's a big win here, especially with rectifiers, right? We have PN junctions, so sometimes there's not that much you can do about to reduce the power losses here. So if you have 20 or 30 watt power losses and things like that, and you can get 1 Kelvin per watt here, that is actually a substantial gain in reliability, and of course a reduction in temperature, or a gain in current, if you want to call it that way here. So we're quite happy about the performance we can achieve with this package here. One last slide here. This is on the topside cooling package here. This is a complex slide with lots of data here, so I'll walk you through it a little bit here, but this is also a reminder here. So what we did here on the right hand side, this is a bridge rectifier. This is a typical PFC, a PFC boost converter here, and we're measuring diode 1 here, and we're comparing two similar diodes here, the fast recovery diode. We're comparing the topside cooling package with a D-square pack here. We're using it in an American circuit, so we're seeing here that the input voltage is 110 volts, so you have a higher current here to reach your power factor correction here. So you really have the low line here. If you look at the, and it's the same die here, so if you look at the efficiency here, I'm not going to go through all the details here, comparing the topside cooling package here with the D-square pack here, the topside cooling package is better. Now with that, with the same die size or with the same die size or the same product, it's of course to reduce the temperature here, and that comes back to the earlier slide we said here, is that the QRR and the IRM, the peak recovery current here in a PFC circuit or hard switch circuit here, has a positive temperature coefficient of QRR. So this always is a good reminder here. The lower you can keep your temperature in this case, the better here, and you will have actually efficiency advantages here, apart from, of course, reliability advantages, that you will have a lower junction temperature here. So this is a typical example of a hard switch circuit here, where this type of device can give you a lot of advantages here, not just in the improved thermal resistance, but also in mitigating the positive temperature coefficient of QRR. So a lot of information here, and let's take a break here and have some fun for a while here, because everybody's talking about topside cooling packages here, and it's promoting them, and they say it's state of the art. And rectifier folks, even though we only make PN junctions here, we actually have made topside cooling here for 40 years here. This is a bridge rectifier. If you don't recognize the GBPC bridge, the thing here, this is the metal here on the bottom here. What you see is the metal here. This is the lead frame soldered to it, and here with the die in here, and this is the epoxy which you put here. So we've actually been making topside cooling for quite a while here, and you can actually get very good thermal resistance here with this package here. The only downside here is that these things are, believe it or not, in the age with robots and 12-inch manufacturing fabs, it's very difficult to automate this. So this is a fairly manual assembly line here, and it's difficult to get ASCQ qualification specifically on the humidity here and the epoxy here. And avoiding humidity coming into the package here. But we can have molding bridges here that can pass ACQ qualifications here, so that is not an issue here. Anyway, that was just a quick break to have some fun here. There is sometimes we think it's new, but there's nothing new under the sun. We're doing topside cooling for 40 years here, and people solder these things on heatsink here and put electric clamps here just to get the connected 30 amp current or about 60 amp current or something, whatever it is, it's single phase. So some people do it also at 3-phase. So this is what is available on the market already for a long time here. Yeah, calling bridges, there's this is our overview of bridge rectifiers here. There's nothing really new here. Two things to point out here. These bridges are 20, 30 years old here already for a longer time here. These were added, so if you have a flyback converter, you could use surface mount bridges up to 20, 30 watts in the old days here. Now you can use them maybe to 50 watt if you're pushing it, maybe a bit more, things like that. Because these things, for example, this one doesn't have any leads, so it's got a very good thermal resistance. And if you put a bigger die in there, you can also have a much higher surge current here. For the rest of the world, the rest of the bridges, there is not that much new here. The main thing new here is that you can actually have planar devices in here. And actually, what happens here is that the VF of these devices will be about 50 millivolt lower here. So that's, some people that use platinum, or standards or something on efficiency here, the bridge rectifier will forever have a 0.6% or loss in the total efficiency here. You can just gain a little bit here with these planar devices here. So that's one thing we were actually introducing to make a slight improvement here, and it's a little bit cheaper than going to maybe a different topology, eliminating the bridge or a bridges rectifier. So this is something also to keep in mind here, what is an option for you. So now we're going to the package product positioning here. So let's talk a little bit more about our packages here. So the first time is why are we doing this? We're introducing a ThinDPAK introduction without a middle pin here at this stage of the life cycle here. So the DPAK here actually has a middle pin here that is annoying if you're having, it's usually okay if you're having on a single phase here, design here, on a 400 volt DC, things that it doesn't cause any problems or puberty clearance, but it might if you go to higher voltages here. So we want to increase this middle pin here. We've already done it on the D square pack here to improve frequency clearance here. That is, if three people want to, for example, on a 3-phase system, want to use 3 single-phase systems with discrete components in parallel with each other, for example, this could be an issue here. And also in some other applications, it's an advantage here. So the middle pin here has actually no real purpose here. It just, the design of the lead frame and where you cut the lead frame in the past. So it's actually easy to eliminate, but you actually need to make a different lead frame, which then needs to be qualified and different investments and the whole lot here. So this is, we're introducing the ThinDPAK here recently with a line of fast efficient rectifiers. We introduced those last month here, and coming up in Q2 is a line of Schottky rectifiers in this package here. Why? That's a good question here. Let's look at first and for all the ThinDPAK here and compare it with the SMC here. So what you see here is a simulation here. I'll go here to what we're trying to simulate. You have an ambient temperature of 25 degrees C. You're going to dissipate 2 watts here, and you're mounting it on an FR4 with 16 by 16 millimeter pads here. So 16 by 16 millimeter, asymmetrical for the DPAK here, symmetrical for the SMC. And so you're mounting that here, and you're trying to simulate here. The construction here, I'm going to talk a little bit about construction here, because whether you compare this device with this device or other devices in our product portfolio, actually here, it's all the same here. So you have the die here, and the cathode here is soldered in the DPAK to the exposed pad here, which is then has a short lead out to the device here. What happens here is the anode here is connected to the other side of the lead frame here, and the heat is coming out. Well, not the heat is coming mainly out this way here, things like that here. In the SMC device here, what happens is you solder this on the lead frame, and the heat goes all the way from this lead frame like this to the PCB here. What happens actually is it's good to imagine every millimeter you add to the PCB or to the heat flow of the device adds thermal resistance here. So this is actually a long path to the PCB. This is a direct path, not only here, but also straight through it and things like that. So obviously the package, or this package construction is preferable over this package construction from a thermal resistance here, from a package thermal resistance here. So that's what we're trying to simulate on the next slide. When we go to the simulation here, one more thing I want to point out to you, the epoxy thermal conductivity and the lead frame thermal conductivity is quite different here. Epoxy is not a good heat conductor here, so the heat goes through the lead frame to the side here and not through the package here, here. So if you want to measure the temperatures, you better do it on the lead here than you do it on the package here, or get an idea here to calculate temperatures, the junction temperature here. That's something else you need to be aware of. The surprise, of course, I mean, after this, you're not going to be surprised looking at the simulation results here. If you do this on the 2 watts here, the ThinDPAK is about 28 degrees C, lower than the SMC here, 2 watts. So we're talking about a difference of about 14 Kelvin per watt here that we can gain here with the DPAK here. So it's obviously a better suitable here than the SMC when it comes to a lot of power dissipation once you go up in power dissipation here. So let's go to this here. So this is why we're adding it here to the product portfolio here. Now, if you look at our product portfolio here, and we're going to go through it here, you can do the same with every package here, and we're also going to talk about the limitation of what we just did here, because it's not only one way, there are also a couple of other things that you need to actually keep in mind here. So what you see here, you can have an SMA, and you can do the same exercise here. This is also got a flat lead here, and you could go to an SOD128 and improve the thermal resistance of the package here. Great. You can actually go from an SMC here and go to an SMPC here, similar as with the DPAK here. Great here. So you can reduce also the thermal resistance of the packages here. And of course, you have also these exposed packages here, also in smaller packages here. So these are all theoretical advantages here. We're going to go from the left, the micro SMA, the SOD123W, and the SOD123HE. They're not necessarily a new package, but they're newer than some of the other packages around here. Some SMA is not recommended for new design. SOD128 is also a new package, maybe limited or to a certain supplier here. SMA, SMB, SMC are the packages introduced 30 years ago and well known in the industry. And also the SMPC actually is also a little bit newer here. And the D2PAK and DPAK, of course, have also been around for ages and ages here. So why is this change from this here to here, or from this package here to this package? Why is it not happening? It's not happening for 3 reasons. Well, it is partially happening here, but there are 3 things to think about here. Why all packages in the long term will be there. The number 1 is creepage and clearance here. So these packages with exposed pads here, these 3 packages here with exposed pads here, they're great for automotive applications, 12 volts applications here, even if you have high voltage surges. And they're also great, for example, on the secondary side of a flyback converter. So we're a lower voltage, like 24 volts or 12 volts, things like that. So these packages are great, but on the AC side, in a 400 volt DC packages environment, they don't work. So this is the one reason why the conversion is not going to happen. The second one is, let's go back to the simulation here. The 16 by 16 millimeter solder pads here on both sides is, of course, a huge space here. In a lot of occasions, or in a lot of designs here, people use the minimum recommended solder pads, which are a factor 50 smaller or something like that here. If you use smaller solder pads, actually the overview of the total thermal resistance here, the thermal resistance of the PCB is going to be 80 or 90%. The thermal resistance of the package is going to be 10 to 20%. So you can improve the thermal resistance of the package, but it's not really going to make a big difference in your design. You're not really going to see that many results here. So that's the other thing to take into account. The third thing is that the automotive industry has switched or is now completely maybe on reflow soldering. But in a lot of industrial applications or any commercial applications here, there's still a lot of wave soldering around. We all know there's a transformer. We all know there are the electrolytic capacitors. So we all know that there is a wave soldering side, wave soldering operation here. And maybe the wave soldering side is attractive for rectifiers because you have some space there where you can make bigger solder pads to get the heat out. So actually, so actually wave soldering is around there, and these J-bend packages are just better suited for that here. So that is what, the situation we're in here, and that's why all packages here that you see here have a long-term future. Let's go a little bit look here and look at it again here from here. The semiconductor people, we on the left versus you here. From the semiconductor people, of course, we distinguish application between transient thermal impedance. What happens is all the power is dissipated in the die if it's less than 1 millisecond or 1.5 millisecond, depending a little bit on the die here. So that's not just TVS here, but that's also, for example, in a flyback converter, the S1 here sees hardly any current here. It's just a surge current that is important here. So we think transient thermal impedance, we take the same die, put it in a small package, and then we're all set. So this is the way we think here. Thermal resistance, of course, we try to improve the package thermal resistance, but it's only part of the system. The main system is determined by you and your design here. We try to reduce the package height here, but the routing is also determined by you where we put it here. The most important thing is, of course, we committed to zero defects here, and that means process improvements here. We've, of course, not just the new packages have these process improvements, but so do SMA here. The main process improvement I'm going to talk a little bit later on is going to be the solder voids here. Of course, you have the different application here. You're going to wave or reflow solder here. You're going to have determine the cost of your PCB, maybe important. Some people are very cost driven here and have lower cost PCBs. For some people, power density is important. For others, it isn't here. And of course, whether the amount of power dissipation you use will determine the amount of package shrinking you can do here to a certain extent, combined with a PCB cost here. And a lot of people route on the wave soldering side anyway, and then the height doesn't become that much, or the height may be important here, but then you also want a wave solder here. So that's of course, these are the trade-offs for all these packages here, why things are not so easy to do here, and that's where we're going here. So I've made a different analysis of all these packages here. You will see that in the handout of the slide here. You can read them carefully and things like that. A couple of I want to put out there is that the micro SMA, which is a 3.3 like a 3.3 type package here from a space here, is great. It's got creepage and clearance limitations, of course, but it's great for automotive and lower power applications here. It can downsize SMAs in polarity protection here, and it uses internally a copper clip here. What I would like to point out to you is that this package actually on the SOT323 here is quite different from a SOT323 small signal here. What makes a package a power package or a rectifier package is two things: the die attach here, so you need to solder the die to the lead frame, otherwise the heat transfer isn't very great here, and the surge capability isn't very great here. And you want to have the product produced with a copper clip, not with a bond wire here for surge rating here, these small packages here. So it's related to surges and heat dissipation here, and this micro SMA is a great package for lower power applications that still require rectifiers here. The SOT123W has a great feature here to replace SMA when the power capability or the power dissipation is not that great here. Then it will have a great future. Otherwise, the power packages or the solder pads are just going to determine the real downsizing. The solder pads are bigger than much bigger than the package. Then it doesn't make sense or that much sense to shrink the package. Exposed heatsink packages are taking off, but they're not taking off in all applications here. You need to have a higher cost PCB here. So here the takeoff is just a little bit lower here. And what we're saying here, SMA and SMB are actually very popular packages here. They will stay important here. In some cases, it's difficult to improve the power density, especially if you're working on a higher voltage environment here. It is actually quite complex to do the improve your power density here. And also the SOD 128 and ThinSMA are newer packages, but they're not taking off so much here because their advantages over the SMA are limited. There is a better construction and a better thermal resistance of the packages itself here, but that is sometimes lost in the whole scheme of the whole power and power dissipation and the solder pads here. And if they are on the same paths, they do need different solder pads from an SMA actually to be efficient here. You can't put them on the same solder pads and expect to get a perfect performance here. So in summary here, you can contact us for more details about all these packages here. But in summary here, we've invested in the micro SMA and the SOD 123W these last couple of years, the SMA, SMD, and SMC packages. So those have been our investments here to reduce lead times here. And so that is just where we have put our money, let's put it like that. And of course, the DPAK here, which is not on this chart here to complete our product line. The last couple of minutes before we approach the 50-minute mark here. Thermal impedance, transient thermal impedance curves here. This is a very popular subject here. And so I put one here, which is obviously measured on an infinite heatsink here, because we're coming up with a thermal resistance of around 10 degrees C per watt or 12 or something like that here. A lot of people like to model these days, which is fair, but all like to work from home, and so modeling is becoming more and more important here. But what do we do for modeling surges and rectifiers here? What can we expect here? Surges are pass-fail criteria here. So usually, we have here the transient thermal impedance here, and we go a little bit lower here, and we see here 1 millisecond. This curve actually does it up to 100 microseconds here. So people want to model sometimes surges. Actually, it doesn't particularly 100% work here because you might scare yourself. The TJ of 150 or 175 degrees C can be exceeded during a surge. It is a pass-fail criteria. Actually, rectifiers get destroyed by surges at around 400 degrees C. Not at 150 degrees C or 175 degrees C. It is also not a reliability problem if you exceed the TJ during a short pulse here, a one-off pulse here. So that is something you need to be aware of here about the limitation of the transient thermal impedance curve. We also supply Cower models upon request here. The same, of course, here is if you're simulating in the lower time zones here with these things here, the same comment is made here. And then I made a question about accuracy and simulation here. One formula that's there for, I think, not 40 years, but maybe 60 or 100 years or whatever, or forever and ever, is that the junction temperature equals the ambient temperature plus the power dissipated multiplied by the thermal resistance here. There are complex waveforms around here, for sure here, so the power dissipation is not always difficult to accurately guess here, but there's also lots of simulation programs here that can actually help you on this here. But and it doesn't really matter here. This formula doesn't matter here if you use these curves here, these transient thermal impedance curves with duty cycles of 0.2 or 0.5 or something like that here. It essentially does not change this formula here. That's what you need to understand here for in a steady state. What you want to, if you simulate a steady state, you simulate surges, they make, but then it's a pass-fail thing. The accuracy of this thermal resistance junction to ambient, you have to watch out here, right? Because the datasheet values are sometimes on 5.5 millimeter or centimeter big solder pads here, or on minimum solder pads here. So there's a huge variety in this thermal resistance junction to ambient here. So this is, you have to watch out because this is actually where you're going to have the biggest surprises here in this whole equation here. And whether you're simulating this with very fancy transient thermal impedance curves with all these duty cycles here, it essentially does not change this formula here. So that's something you need to be aware of. If you want these curves, we make them upon request, so we're not stopping people from getting them or something like that. But that's why we're not going to make them, or we don't have them 100% available at the moment here. The next two slides here to finish here is a So we've added so we are committed to, as a rectifier supplier here, to zero defects and zero PPM. So that's our aim. A lot of our business is in automotive. It's our focus market here. And of course, we achieve that also easily here. The only thing that is not tested in mass production is this surge rate. This you need to be aware of here. So it's guaranteed by design, not by tested in production. And of course, the 8.3 millisecond is something also from 40 years ago, the days of 60 hertz linear power supply. It's far gone. The newer data sheets have 1 millisecond, as we explained before, which is maybe more relevant to your current design here, things like that. Beware when you convert these surges using I squared T. It's not a bad way of doing it. It's not a wrong way of doing it, but the VF changes with the current, right? The VF of the diode at 20 amp is not the same as the 10 amp here, and the current here or the time here, you may be also entering in a different area of the transient thermal impedance here. So there are limitations. It's an approximation, but it's a good approximation to start your design process here. This thing here is the failure mode here it's not testing here, and it's guaranteed by design here. The failure mode is essentially solder voids here. And not every supplier, we control the solder voids in all these surface mount assembled packages here, but maybe not everybody does. There are maybe some older lines that do not control the solder voids here. So this is something to be aware of here in your when you choose your supplier for rectifiers. The last thing here, we not want to pretend that diodes are high-tech. They are PN junctions and nothing more here. A few things here that you cannot see the data sheet here, and where you have to actually sometimes also trust your supplier here. Obviously, if you second source them, the efficiency may be different, especially in switching applications here, between different Schottky diodes here. The thermal data and the junction temperature in the real system needs to be measured here. There are maybe some differences between suppliers here, especially when it comes to die size, which can always impact the cost. So that's another area we need to watch out for here. EMI is another area which is never going to be the same here. And then a couple of other things here that you need to be aware of. The first thing is different test programs by semiconductor suppliers here. If you commit to zero defects like we do, you need to have path testing, path average testing here. Data sheets of semiconductor rectifiers are 50 years old. As a result, some of the spec limits are very wide, like 5 microamps or things like that, whereas the real leakage current is in the nanoamps here. So you need part average testing here to get reliable devices here. Different process technology should be evident. Not everybody uses the same processes to make those things, even though everybody says they're GBP. Different distributions on key parameters and CPK. That's more an issue when you look at Schottky diodes, for example, here, and efficiency here. Then the temperature cycling, the last lines here is, second to the last is here, of course, related to solder voids and elimination of solder voids here, which is a critical thing here and can only be done with more modern equipment, especially the surface mount devices here. And the last link here or hint here between suppliers is that on bridge rectifiers, there are some people that try to save a cent on saving some copper in these bridges rectifiers here, which then have asymmetrical designs or actually poor temperatures or poor temperature distribution here. So that's another area where you may want to pay attention to when you choose your bridge suppliers here. That's it here for our rectifiers here. We'll go to the Q&A section here, and I will try to read your questions here. Before we do so, however, is if you thought this rectifier was of interest here, this webinar was of interest here, you want to know more about our products here, when you get the follow-up link, there are 2 ways of following us here. The first is the Component Engineer newsletter, which we roughly produce every 2 months here, which updates you in detail about our products or new application notes or other things we are doing. The second thing which we are actually also doing is via LinkedIn. On LinkedIn, you can also follow us. We have a few thousand followers and that type of stuff to keep updated about our company here. So that's our email address in Munich, where you can reach us, or via your known sales contact here. I'm going to go now to the control panel here to see if I can find questions here. Please enter your questions here and I will try to find them. Sometimes it's not so easy to find them, but if I do not find them, they will be all recorded, and the recording is available after that. So I'll look at them and I will reply to them either tomorrow or on Monday here. Let me check where I can find the questions. So I cannot find any questions here. I'll wait for another 30 seconds before turning off the thing here. If you asked a question and I by accident missed it, then please don't worry. I will actually find out about it later on and I will reply to you later on. So in this case, I will actually now will end the webinar. Thank you very much for your attention. Apologies if I missed a question here, and we will get back to you if you did here. Thank you very much for your attention and have a nice afternoon. If you're in Europe, there are also people from Asia and the US logging in here. Have a nice day if you're from the US here. Bye-bye.